device for VR simulations. Jorg, are you online?
You hear me?
Yes.
Okay. And okay, I guess I saw it as in half an hour that I would be presenting. So let me slow you down just for a moment. I don't quite know how to share. I don't ever use Microsoft Teams. I don't know whether you can actually see me right now. You can, but it shows more of.
All right, I'm muted, so I can see you right now.
Yeah, you can see me, but actually you see much more of the messy room than I wanted to show you.
Not a problem.
There
so
we
on
go.
the top right, there's a share option.
There's an open share tray I can see.
Yes. So go ahead and open that.
And
then you get to pick the window, or if you want to share the entire desktop.
Excellent, excellent. Okay, so let me just make this here. See format slide. Yeah, this way you see it is not unduly prepared. Let me see that I get. It is the desktop, but why am I seeing this screen? This is not the one that I want to share, but you get to see it nevertheless. But if I pull this over, you're happy.
All right. All right. I see your presentation.
You see my presentation? I can't see myself anymore, and I can't see you. I hope that's not a problem.
Not a problem at all. So if you want to maximize it, put it in view mode.
Let me make this large, and then we can get started, provided you allow me to go all the way back on this one here. How do I get back? Sorry. Here. Okay, this was my talk in reverse and fast. Okay, good. All right. Now we can get started. Sorry for the slow motion there.
All right, I think we're good to go.
And let me, okay, I can hear you. So I don't know, there's a good number of people in the audience. So I don't know what you expected. I have done some work with VR with head-mounted display for modeling in 3D. It's something that's ongoing work, and we'll be very happy to collaborate with people. I'm coming out of geometric modeling originally, and splines in particular, with Carl de Boer being my advisor way back when. And so this is something that I thought might just be useful for someone in the audience. And they may say, oh, I can save myself a lot of headache, much more than dollars. So this is a 4 degree of freedom device that you can use with your VR simulator. And I have a very specific context in that. And these are the people who worked with me. So there we all are. I'm Jorg Peters, obviously. So this is the context, and you're still good. You can see my screen. You can hear me clearly, or should I improve anything?
Everything's coming across just fine.
That is fantastic. Thank you. So so here you see this gentleman staring into the far. That's because he's actually doing laparoscopic surgery, and he's looking at a screen that you can't see because that's where the photo is taken from. That lady is also looking at that, but she or he is looking at this screen so you can see what they see inside the body. Again, this is called laparoscopy. You put a lot of gas into the abdomen, you inflate, and therefore you have enough space to work around with it. And these are little chopstick-like tools that allow you to cut, cauterize, tear, and whatnot, and staple and whatnot. So you've probably seen such pictures before. Now the question is, and the context in which all of this came up was, so how do we train doctors who initially only work with props, with plastic props, and then go to the real person? What will we put in between? And that's sort of a classic thing that has already been solved. There used to be many providers that provided these force feedback. Well, that wasn't their job. They provided training, and they needed to have some force feedback devices and 4 degree of freedom input devices. And so you see, this is a commercial product, and I'm not advertising it, but at the moment there's only one company left. They have bought each other up, and so you don't really have a choice if you go out there. If you wanted to do this kind of laparoscopic training, you have to go to surgical science. There is an alternative, and that's a little bit more home-baked, and that's not what I'm trying to tell you here about the 4 degree of freedom device, even though this is a 4 degree of freedom device. So this is our home-baked setup. Note these little robotic arms that are very popular, that you possibly have seen before. And here's again the laparoscopic view on a regular monitor. And so these are 3D printed, and again they have 4 degrees of freedom because you can turn them left, right, and you can turn them about their own axis, and that's connected to this robotic arm, and you can push in and out. Those are the 4 degrees of freedom. If you wanted to see what that looks like, you can click on this here, or you can later on look up my name, Jorg Peters, and SurfLab, and tips will also do the trick. The point is of our thing here is that it is surgeon authored, and you'll see an example of what that means. That means you don't get a training unit, but you actually have surgeons who create new training units for their need. And it's essentially a software effort, and so this here was actually a pain for us to maintain and to create, and you have drivers and you have to 3D print and whatnot. So we really wanted to actually move away from that. And so here are the different choices that you have. This one actually wouldn't do it. And the big problem is that this gentleman here in the early version doesn't have this restriction to 4 degrees of freedom. This is at this point here a 6 degree of freedom device, and that teaches the wrong methods. So this is no good. 4 degrees is all you get, and that's why we have this here, and it's painful because it has all these printed parts and whatnot. You can buy something, but again, it's not cheap, and it also has its own drivers and whatnot. So what is the whole context? This is all still telling you the context, and then I'll give you the 4 degree of freedom device that you already own in a moment. So just for context, let me play this back. I can make it larger if it's too small for you. So our surgeon author types in the pieces, the parts of the procedure, the anatomy, and then things like grasp, gallbladder with the blunt grasper, and then there's some error messages that or safety concerns that you also enter into that. Then you get a whole list of these things that are also given to the trainee, and so you can embed all sorts of things, and then you get a preview of the anatomy, which gets loaded automatically from a database. And the interesting thing is this is not just geometry, but this is physics, as you will see in a moment. So now comes the part that where this input device comes into it. So as you move your hand up here, you move the tool inside, you get force feedback in the process. If you cauterize, like just a moment ago, if you cauterize on a vein or artery, that's not a good idea, so you get minus points in your game. And if you don't put in
Oh, let me send my message.
How long ago did my microphone cut off?
Maybe about 30 seconds ago.
Okay, I don't know why it did, but there it is. And so in the end, you get some feedback as to how well you did. But the critical part is, as you move this 4 degree of freedom device, you have this interaction. So this is the software that we're really interested in, and having the hardware component here is for us in some sense just a distraction, even though it was fun to build it. Okay. So here comes the solution, sort of, the Swiss Army knife. So this came about, it's 21st century Swiss Army knife. This came about because, well, several things. we found that when we deployed our fancy setup, we would get very few of the residents to actually use it, which is no worse than what stood next to it was a $200,000 commercial training simulator, which also didn't get used. And the thing is, these people don't have time. They want to do it when they have time, at home or elsewhere or in the cafeteria. They don't want to run over to the special lab where all these things are put out. And another thing that annoyed us to no end was that they would break things, and while it's not far from where we are on campus, they wouldn't tell us that it's broken, and you check a week later and you find that nothing is working anymore. You have to rebuild it. So this idea came to me at the beginning of COVID. We wanted to send things out. We wanted people to use by themselves at home. And so here's our 4 degree of freedom device, which is actually very simple. So your generic cell phone has already 3 degrees of rotation. This is what you can do inside the body. You can take the tool, you can rotate it up, down, left, right, inside the body. You can rotate it about its own axis. That's the green one here. And you can do the same thing with the cell phone. Now, why do we flip the cell phone upside down? Because we need in and out needs to be super precise. The cell phone has roughly the same distance or same length as the body cavity inside, the abdominal cavity when it's blown up. So if your cell phone is on the order of 3 to 4 inches long, is that roughly right? 3. Then moving your finger up and down is about the same amount of length as the tool would travel inside the body. So this is a very nice match. The one downside is that if you use one hand to hold your cell phone and the other hand to go in and out by running your finger over it, it's very unlike the real surgical tool. And it's you also can't use your second, well, you need a third hand then, which is no good. So what we do is we actually take a cell phone pen and we fix it at the bottom. And now you can use this as your pivot point, just like the trocar point was for the surgical tools going into the body. Mind you, why don't you have the horizontal and the horizontal directions to move in? Well, you'd rip up the body if you were to move the tool in and out, right? Not in and out, but if you were to move it in the sagittal or coronal plane, actually, it would be for the body. If you moved it in the coronal plane, you would, well, you can't because you only have a hole to go through. Anyhow, so you affix this cell phone pin, and now you can move in and out by moving this. We added a little more. You want to have tool actions like cutting, cauterizing, tearing, applying clips, and the whole shebang. So that we do by pressing the volume button, and then we have the modulated vibration as instead of the force feedback. So that's our poor man's alternative to the $5,000 worth of force feedback devices with their attachment and whatnot. Okay, so is it any good? First challenge, how do we align and calibrate? Now, given my audience here, I don't really have to explain that. You use quaternions, right? You have a global coordinate system. You have the coordinate system in user space. You make the user point to the screen, and then you translate that into the internal coordinate system where you actually solve the differential equations in real time. By the way, this allows you to cut fatty tissue, and so the fatty tissue will behave differently once it's cut than when it was not cut, and it has, you can pull things back and so forth. But of course, for the cell phone, you wouldn't experience that kind of haptic feedback. You'd only get the vibration on how much you have actually pushed this, and you will see the result in the scenario. Okay, so that was the first challenge to be done. The second one is, how do we get this 4-degree of input device into people's home? Because there's also the question of setup. Well, we do remote gaming setup. SOFA is the program that we're using for solving partial differential equations in real time. So there we have well, it's still a desktop, but it's has a good graphics card, and it's a good machine. We have a server put on top of that talks via the internet to a client. So you can walk in with a tablet or with a laptop, and you can actually get the whole simulation onto your laptop. Nothing new about that in some sense, except that we had to build it ourselves, and so there it is. We measured a maximum of 0.1 seconds. That's, of course, is not haptic feedback, but in this case you don't need the haptic feedback. It's pretty good in terms of latency for what you do with your hand, and you can't. So it is actually it's good enough for what this is doing. One can adjust to that. The other thing is, of course, here's again our cell phone pen, our cell phone, and we have to send both the collision signals in one direction and sensor data in the other. And so we have a client that sits on this laptop or whatever you have as a display device. So this is a thin client, as an STHIN, thin client. And and that was our second big challenge, how to get the communication right. And the third one turned out to be getting it across platforms. It turns out that people in the medical arena have lots of iPhones, and then they might have Mac OS on their laptop or Windows. So we had to make these guys talk to each other. In particular, Bluetooth is not what I thought it was. It's not a standard. It differs enormously. The Bluetooth on Android and the Bluetooth on iOS need completely separate coding. So now we have of the 4 combinations, Mac OS with iOS works, Windows with iOS works, Android with Windows works. We haven't bothered with Mac OS and Android. All right, so what does the whole thing look like? Let's have this, maybe we can even make it larger. See, no, it doesn't want to. Okay, so what we're seeing here in green is the cell phone pen put up. By the way, am I talking too fast? Are there questions?
No, you're doing just fine. Please continue.
Okay, thank you. So here's the cell phone pen, and it's put there upright so that we're going to use that in a moment, but we have to first start. What you do first is you look at your laptop. There you do the connectivity. You see that 2 items are still in red. They're going to turn green because of the connection taking place. So that's your thin client. Then you have your app on your cell phone. So it's just a downloadable app there. You see the person, well, it's actually us doing this, and you press that you want to join. And you see something changed over here. So now this means that the cell phone talks to the laptop. And then we have one more red, and that will hopefully also turn green in a moment. And there it turned green. Now our thin client, the laptop, talks to the server. And so this is the setup for this 4-degree of freedom tool. All right, so for your own data, you type in where you want to set your data set to. And what we saw a moment ago was all done with force feedback devices, and this was done with the force feedback devices. The left hand, what you just saw here, is the weak hand in our case. You can switch the 2 around. So the left hand is only used for grasping and pulling tight, typically. So here the gallbladder is being pulled so that you can easily cut the fatty tissue. And so this is done actually with the mouse, because we found that very few people have 2 cell phones. And having 2 cell phones with different iOS and Android on it is a nightmare. So so that's done with the mouse, and you see it's sort of it looks like a cheap tool, which is intentional, and so it just stretches it. And now the cell phone is being flipped over. So far we looked at it and typed onto it. We had a join and a calibrate station. And now we put it upside down, you see. Can you see that? Is that large enough for people to see? And this is unavailable. We could just go to the YouTube movie if you wanted to see it afterwards once more. What did I do? I clicked in the wrong place. Okay, so we're starting now to cauterize. That means we're burning away fatty tissue. And all of this is, of course, real time. And you see that here you see the mouse button in green. So that's being pressed so as to have the action. If you don't press the mouse button, it's not the mouse button. If you don't press the volume button on the cell phone, then you don't get the cauterizing effect. Just like in the real cauterizing iron, you need to press a button to make it burn away small vessels and fatty tissue. Okay, wait a second. This is annoying. Let me go back. Let me go back. How do I go back there? There. Okay. And let me try that again. Fortunately, I remembered where we were. Okay. So we do this once more. There's nothing wrong with spending a little more time on that. And so here we cauterize by pressing the green button. You see that at the bottom there. Okay. So you expose both the artery is at the bottom there. We expose it. And of course, you have to be careful not to directly cauterize the artery. So that's called freeing up. And in the end, what the goal here is to rip out the gallbladder, which is cholecystectomy. And so you see the hand moves, the tool moves, and do we want to move ahead? We place the clips. That means we change our tool tip. We actually cut in between, and this is done correctly. So we get a green tip there because we left two clips in the body. So that's correctly done. Of course, you can't drop any. That's a really bad mistake. That costs you a lot of insurance money, dropping a clip. And now essentially the remainder here is I don't dare to click to bring us forward, so I just let it run because that always makes us jump. So basically you do the exact same thing that you saw a moment ago with the more expensive setup. So basically what we've done here is we've gone from $200,000 to a $10,000 setup to, if you already own your laptop and a cell phone, to a $0 setup. And there you get your feedback of how well you did. I think this here we can move very quickly over it. It's just same thing. Here's another way to have your cell phone pen set up. And you see how the hand moves and how this moves. It's just more clear how that works. And again, the same scenario. Okay, and this is my presentation. So this is all about a little fun experiment. And if you wanted to know more about it or had some thoughts about it, as I say, right now I'm more focused on HMD, virtual reality head-mounted display stuff, where we want to actually do 3D modeling in there from anatomical data. But it could be anything that we get DICOM and model tissue with it. And so here, this was just as a hopefully interesting input of an input device. Thank you.
Right, so we do have one comment in the chat session. Joseph, do you want to verbalize that, or do you want just to read it?
Yeah, very nice work, Dr. Peters. As I said in the chat here, when the simulation is so good and so close to reality, when you actually do the surgery after being trained in a simulation, it seems actually easier in many cases. So really nice work you have.
Yeah, so as I say, the real goal of this was to allow surgeon educators to actually create the whole scenario, which is, I think, something that many of you would be very interested in too, that basically you have a small interface at the beginning that gives just a subset of options, given that human anatomy is quite finite, but you probably have similar kind of ontologies. And then the specialist doesn't have to think about modeling, but just grabs the pieces, throws them into the scenario, and you can get going with this kind of interface to actually do the simulation. So if you want a different part of the body than the gallbladder, so we have many other scenarios that are basically put together initially in Blender, and then you're ready to go.
Yes, in medical school, we used to call it see one, do one, teach one. So once you do this and you get the muscle memory and you see it done right the first time, it's really nice. And then I can envision where you potentially could use actual images and structures from an actual patient, you know, with an MRI or a CT, and reconstruct those objects and put them into your.
That's exactly what we're doing with our VR environment. Yes.
Really nice.
Yeah. So that is not yet done. DICOM images of MRI are, you know, it's a learning experience to interpret them and set them up right. That's why you have radiologists. So, yeah, basically it's a pipeline that allows you to do that. We actually got some also negative feedback on that, in the sense that we don't want surgeon educators to actually create these modules, because we want it to be fully vetted by the association, and only top surgeons are allowed to create these things, and maybe top companies to go with it. So there is a concern that people are being, yeah. But I think of it as like desktop authoring. People said, oh, you can't possibly have people typeset what is finally published, and now everyone typesets their own stuff on the internet anyhow, right? So yeah, I hope that this kind of environment is something that we'll find like an open source environment distribution, and with this 4-degree of freedom interface now, it can be rolled out to just about anyone. Our current bottleneck is that we only have one server running, so we need a server farm at the back if 50 people want to use this at the same time. But all they need then is a laptop and a cell phone, and a pen, unless they want to put their finger underneath.
Yeah, and we do have one other question. David?
Yeah, I was just wondering if you, and you sort of answered it, but did you find that the students use the system more, or more likely to use the system when it has an easier setup or an easier ability to do it at home or something?
That is absolutely correct. And I can't give you numbers yet, because that full study isn't done yet. But definitely, I mean, getting residents into this special room that is, for us, is at the Veterans Administration building across a busy street, is hair-raising. And as I say, they break it. So this is, if they break anything, it's their own it's their own pen and their own cell phone and their own laptop. Okay, so yes, it's a big boost, and it allows us to concentrate on the software component.
All right, we have, go ahead.
Yeah. Oh, yeah. So SOFA is actually open source. It's a simulation open framework architecture, even though it might seem like something like a couch. So far, if you look it up, is from INRIA, the French outfit, and it's actually quite nicely maintained. They have two full-time people who are looking after the open source software, and lots of contributions. So it's like an early MATLAB was when people were contributing and it wasn't yet something for sale. So the heavy lifting, we've added one module to it because we had, so they didn't have good plasticity, which is used at some point in surgery, plastic stretch so it doesn't come back. So we added that one into it, but otherwise it's all modules written and tested over time by an open source community. And they are the ones who allow us to do this in real time. Well, there are several parts. It's also the communication that we, of course, had to write, but the original, so it gets fed with XML, and you have to know what you're doing. And so Blender sends models. You create a Blender model, you can then generate XML. And we also create files that go into the database. And then you just pull that data set down to and start SOFA on it with some slight specialization. So we have a few add-ons, but small ones. We want to keep it as small as possible. And the bulk is all C++ open source from INRIA SOFA.
Well, thank you very much, Dr. Peters. Definitely a very informative and interesting presentation.